Hi, everybody. This is Mrs. Clayton. Happy Monday to you. Good morning. Hey, I just wanted to apologize. I'm not here in school. I'm at the doctor's. He's looking at my foot. Hopefully, I can get my boot off, and today would be a good day. You guys have Mrs. Kreifels with you today. If you guys remember, Mrs. Kreifels, I've told you this before. Mrs. Kreifels is the former science teacher at Platteview Central. And so she understands phase change and she can help you if you've got any questions throughout this lesson. Please raise your hand, have her stop the video, and then she can answer your questions and help you clarify so you're ready for the test on Wednesday, okay? All right, let's take a look. You'll notice that I've added a new folder. This one's for February, so all of our February lessons will be in this folder. We're going to scroll down to Friday and Monday. So let's take a look at your objective for today. All right, today the student will be able to explain how molecular attraction, this is a new vocabulary word you're going to have today, how molecular attraction interacts with energy transfers to determine whether or not a phase change will occur. I have a really good sense of that you all understand what happens on a molecular level when there is a phase change. And so the only piece of the puzzle that you're missing is understanding this phrase, molecular attraction, and how that plays, what part that plays in an energy transfer. So instead of taking 4 days to do all the lessons in chapter 3, I just kind of combined them all, put them in a chapter 3 slide. We're going to go through that today. We've got some activities for you to finish. And then the rest of class time you will be able to use to prepare for the end of the unit test. This will be for you on Wednesday of this week. It will be 18 multiple choice and 2 short answer questions. So it's just an amplified test. You guys know what those look like. 18 multiple choice and 2 short answer questions. Okay, let's go ahead and get started with the lesson. This first slide is just to remind you, if you have not done so already, please hand in your phase change scientific arguments into the white basket. It's on the table there at the front of the room. And if you don't have a hard copy, if you did not print one off, that's okay. I don't want you to go into the computer lab and do that. Instead, email your document to me and I will print it off. Listen, I said email your document to me. Please do not submit it to Schoology. There are like 5 steps I have to go through in order to print from Schoology. So it's so much easier for me and quicker for me if you can just email those to me. This is the last grade before your parent-teacher conferences. And actually, I know grades are being printed off today, but I will have these graded and added to your final score that I communicate with your parents for parent-teacher conferences. So please make sure that you hand that in, okay? I'm going to let you pause this video and you're ready to begin. Just go ahead and start it up again. Okay, so I'd like you guys please to log on to Amplify. We are in lesson 3.1, so chapter 3, lesson 1, and we're going to go into the warm-up, but we're going to do something a little different. I don't want you to actually do the warm-up yet. We're going to just read the email. Don't launch the simulation yet, okay? So Dr. Flores sent us an email, and there was somebody who posted on the forum for the Universal Space Agency, and they need our help. So we're going to read the post and then complete the sim activity. We're going to do the sim a little bit differently, okay? So 2 student chemists from Galileo, and the subject is question about lake evaporation. I read your findings about the lake. They're referring to your scientific arguments. But I am confused about the argument that the lake evaporated between 2007 and 2009. The evidence shows that Titan first started getting hotter in 2002 when summer began, but the methane lake was still liquid 5 years later in 2007. If the temperature increased starting in 2002, then energy was being transferred into the lake. Why then hadn't it evaporated by 2007? Great question. Let's just review real quick. In chapter 2, you used evidence to develop the argument that the lake on Titan evaporated. And you figured that out because all the evidence said that energy was being added to it when Titan's summer season began. So let's take a look at the timeline of Titan's summer to see if we can understand why the forum user is so confused. So if you guys remember, summer started over here in 2002 and it went all the way through until the end of 2009, beginning of 2010, right about here. So we know that summers on Titan last about 7 years, and it shows us right here that it was about 5 years before the liquid lake on Titan was photographed in 2007. And then 2 years later, there was no lake at all in the photograph. So that means at some point in time during 2007 and 2009, that lake evaporated. So the forum user is confused because they're saying, well, we know energy was coming into this system on Titan in 2002. Why did it take so long for the lake to evaporate? Okay, let's take a look. That leads to our chapter 3 question, why didn't the liquid methane change phase before 2007? So let's just do a little bit of review, you guys, okay? In order for phase change to occur, we have to have some things that take place. There are steps to phase change on a molecular level. So first of all, we know that energy has to either be transferred into or out of the molecules. Second, that will cause either an increase in temperature, kinetic energy, and speed, or a decrease in temperature, kinetic energy, and speed. And that will lead to an increase or a decrease in the freedom of movement of the molecules. So you'll remember that the molecules in a solid are really closely packed together, and so their freedom of movement is very low. But if energy is increased and temperature, kinetic energy, and speed is increased, then the freedom of movement increases, and those little molecules will separate from each other, and they'll have more room to move. And of course, that leads to the phase change. And in this case, it was the phase change from a liquid to a gas, which is evaporation. So I want to suggest that there's actually one more step, and that happens right here in between step number 2 and number 3. It has to do with molecular attraction. Let's go ahead and come back to our analogy of the butter and the frying pan. Remember that when we were talking about that? So if I unwrap the butter and I put it in the frying pan, I put the frying pan on the stove, I turn on the stove, I am increasing the energy, right? Energy is being transferred into the butter molecules. So then does that mean the butter will go from a solid to a liquid immediately? Of course not. You guys, you've all seen this before. You know what happens. On a macro scale, we can see that there's both a solid and a liquid. Remember, macro scale is what you see with the naked eye. So we see that there's a solid here. It's rigid. It holds its shape. And we can see that there's also a liquid here. It takes the shape of the container. It stays at the bottom of the container. So what's going on? How come we have both a solid and a liquid, even though energy is being transferred into the butter molecules? Well, in order to answer that question, we have to figure out what's happening on the molecular scale. And that leads to our investigation for today. Why does an energy transfer not always result in phase change? Now, we've got an energy transfer into the butter molecules, but they don't always result in an instantaneous phase change from 100% solid to 100% liquid. Why not? What's going on? Well, let's figure that out. We need to go to the sim. So I want you guys to go back to Amplify. You guys should be in there already. Scroll down and launch the simulation right here. We're not going to follow these directions. I'm going to tell you what to do. So go ahead and launch that. And when you're there, I want you to select substance A. And if you remember, substance A is a solid. And we're going to go ahead and just play. And I just want to play just for a second. We can tell it's a solid because the molecules, if we just click on one, the molecules are moving in place. It's rigid. It holds its shape. If I turn it on its side, I want you guys to turn yours on the side. It's holding its shape. Okay, we're going to deselect that molecule. I don't want you to see that at all. And the reason why I wanted you to turn it on this side is because I wanted you to create this little space right here. It's going to help us really be able to visualize when this solid turns into a liquid. Did you guys see that little gas molecule that popped off? I want you to watch that for a second. What happens to it eventually? Oh, it gets pulled back into this. That's interesting. I want you to hang on to that, okay? All right, we're going to move it back. And let's go ahead and see if we can transfer energy into this system, into this solid molecules. And we're going to make a liquid, okay? But we're not going to just do it all at the same time. We're going to do it little bits at a time. And we're going to try and figure out why, if we have energy going into the system, why it doesn't transfer from a solid to a liquid instantaneously. Let's take a look. You guys come over here to your energy and you're going to give it 10 clicks, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, take a look. We're going to let it settle there just for a second. And I want you to notice, I'm going to click on one of these molecules again. And we can see that it is still pretty much just moving in place. It's not moving around. But I do have these little gas molecules. My dog is coughing. He's old. He's 15. I'm sorry. Okay, we do have these gas molecules that are just popping off all of a sudden. But then notice what happens to them. They get pulled back to the other grouping of molecules. It's almost as if there were magnets, right? And there's this attraction that pulls the molecules together. That's interesting. I want you guys to notice that. Okay, let's keep adding some energy. We're going to do 10 more clicks. 1, 2, 3, 5, 6, 7, 8, 9, 10. And let's just observe our molecule, but look at what's happening up here. First of all, we've got lots more gas molecules, but they still want to come back. They're still being pulled back. I also have some molecules here that are actually flowing past each other. That's interesting. So I've got some change of phase here. If we would look at this on a macro level, this would be a little bit of a liquid, a little bit of a gas, a little bit of a solid. I'd have all of it right here. Let's add 10 more. And we're just going to let it settle. Lots more gas molecules. Interestingly, when these gas molecules hit, they might bounce off each other, but then eventually they come back. They're pulled back. There's molecular attraction here. And isn't it interesting that it took 30 clicks of energy, of us transferring energy into this system in order for this to change? I would say now it's a liquid, but it's also kind of a gas. That's interesting, right? Take a look here. What we just modeled is this phase change called melting. Melting is when you have some liquid and some gas, or some solid and some liquid at the same time, because it's in between a phase change. Think about, like, if you had a glass of ice water and you let it sit out for a while and the ice melts, it doesn't go instantly from a solid to a liquid. It takes a little bit of time. It's melting. Okay, that's what we just modeled that. So I'd like you guys to take out your good notes. You're going to write down the vocabulary term molecular attraction. Before you do that, please let me explain it. Let me watch it. Look at it, please. Don't write it down. I want you to really truly understand this meaning before you write it down, okay? Molecular attraction is a pull between two molecules that's always the same for one type of substance. Think about that for a second. We just saw that in the simulation. It is a pull between two molecules that's always the same for one type of substance. Different substances have different molecular attraction. I'm going to let you pause the video, write down your definition, and then go ahead and start when you're ready. Okay, so you've got the definition. I'm going to actually have you guys come back to Amplify. We're going to try something different. I want you to reset. If you need to pause it while everybody gets back together, go ahead. So a reset, we're still in substance A. I'm going to play it. And I'm going to really demonstrate this pulling, okay? I'm going to go ahead and not have any energy come in, but I'm going to reach in there. I'm going to grab a molecule. I'm going to grab it and let go of it up at the top. Look what happens. It's pulled back to the other molecules. This is the molecular attraction that we're talking about. I'm going to grab one, pull it out, keep it away, and when I let go, there's attraction. It gets pulled. Like if you had a magnet, two magnets, and you were sliding one across the counter towards the other, at a certain point, that magnetic attraction, the force would actually pull the two magnets together. It's exactly what's happening. Now, somebody might look at this and go, well, you know what? It could be molecular attraction, but it also could be gravity. Okay, let's go ahead and take our gravity. Let's toggle that off. And let's see if there's molecular attraction even when there is no gravity. So you're going to see that your solid's starting to float in space, which is kind of funny. And I'm going to grab one of these molecules in the middle. I'm going to pull it away. And let's just watch it. Don't pay attention to anything else what's happening here. Look at the molecule that you pulled out. There's no gravitational pull. So this pull that you're going to see here in just a second is molecular attraction. Molecular attraction. Isn't that cool? Science is so cool. Okay, we're done with that. Let's come back to the video, or come back to my slides. I want to show you what I mean by this last little part here where it says different substances have different molecular attraction. I've got a video I want to share with you. It's ethanol versus water. I'm going to come in here to YouTube and I'm going to start it at the very beginning. There's no sound in here, which is good. It's going to let us talk about it. So the demonstrator has two bottles. This one's filled with water, and the one on the left is filled with ethanol. Ethanol is a type of gasoline. Okay, so what do you notice about the two liquids? I'm going to pause it here. What's the difference between them? I'm going to stop talking and I'm going to let you guys raise your hand and talk real quick about the differences, what's going on with each liquid. Okay, so hopefully you guys made some observations that first of all, the water is pulled together in kind of a droplet, like a bead. It's clinging closer together. And the ethanol is spreading out. The reason for that is because of molecular attraction. Which one of these do you think has a stronger molecular attraction? It's the water. The water, even though both of these are liquid, both of these have molecules that are flowing past each other. The water molecules actually have a stronger molecular attraction, and that's why they're closer together. The ethanol has a weaker molecular attraction, and that's why they're spread out. So let's go ahead and see. We're just going to make an observation. What happens over about 12 minutes? Take a look outside here. Pay attention to the outside of the ethanol. And you're going to notice something's going on. Keep making a comparison between the ethanol and the water. You're going to be able to start seeing it right about now. What happened? The ethanol evaporated. The ethanol changed phase, but the water didn't. I want you guys to notice they're exactly the same drops. They're in exactly the same environment. They had the same amount of energy being transferred into both molecules, but the ethanol evaporated faster. Why? Well, let's go back and take a look. We've got a couple key concepts here. Key concept number 8, think about what you just saw with the ethanol and the water. A phase change occurs when the kinetic energy increases enough to overcome the attraction between molecules. I'm going to pause and let you write that down, and then I'll explain it. So when we were watching the video, the liquid on the left was the ethanol, and that had enough energy to overcome the attractions because the attraction, the molecular attraction, was really weak. So it didn't need a whole lot of energy in order to overcome the attraction. Does that make sense? Move on to key concept number 9. I'm going to read that, give you a chance to write it. A phase change occurs when the kinetic energy decreases enough so that the attraction between the molecules pulls them together. Okay, what this is saying is when the kinetic energy decreases enough, then those molecules will slow down because the kinetic energy, remember, that's energy of motion. They're close enough, they pull molecules back together. What these two key concepts are saying is, in key concept number 8, we've got energy coming into molecules, right? And it overcomes the kinetic energy. So it would be like me grabbing onto one of those molecules and pulling it out. It overcomes the attraction between the molecules. But then, if energy is being transferred out of the molecules, then it pulls those molecules back together. So, key concept at number 8 is talking about two phase changes. From a solid to a liquid, that would be melting. And from a liquid to a gas, that would be evaporation. Key concept number 9 is talking about when energy is transferred out of a system. So this would be a gas to a liquid, or I completely just I lost my train of thought. You guys say it. Oh my goodness. Why can't I say it? Evaporation and I'm getting old, you guys, and I've done this video way too many times. I'm not going to say it. I can't say it. I can't say it. Oh my gosh. Okay. That's really embarrassing. But then also going from a liquid to a solid, that would be freezing. Why can't I say it? Okay, now it's really going to bug me. Hang on. I'll think about it. Will you guys please go ahead and for key concept number 8, I want you to make little parentheses and I want you to add the two phase changes that this is talking about. So this is talking about melting and evaporation. And then let's go ahead and write the two key concepts here and what those are describing, okay? So let's talk about why we think the liquid methane didn't change phase before 2007. Let's put it all together, okay? We've got 5 years of energy being transferred into the liquid methane, and it does not change phase to a gas. It doesn't evaporate before 2007. So why don't you think the liquid methane, why didn't it change phase before 2007? I'm going to let you pause and think about your answer, and remember, think about your key concepts, because this has the molecular attraction. That's a key phrase you need to include in your answer, okay? Think about it. Okay, maybe you couldn't quite think of it. Let's talk about it. We know that seasons are seasons because it has to do with where a planetary body is in relationship to the sun. We know that they revolve around the sun, and the season where it's closest to the sun is called summer. So if Titan is closest to the sun, then we know that it's going to get more energy during this time. And so therefore, summers on Titan, we know energy is going into the substances. Now, remember, if we have energy going into the molecules, then there will be an increase in temperature, kinetic energy, and speed. And an increase in kinetic energy will overcome molecular attraction, which means that there will be an increase in freedom of movement and a phase change. I'm going to have you guys pause the video. I want you to take a screenshot of this slide. This is really important and something that I'd like you to study to help you understand and be ready for your test. Okay. So, why didn't the liquid methane change phase before 2007? There wasn't enough energy transferred into the lake to overcome molecular attraction. Great job, guys. We've got an exit ticket. Mrs. Kreifels has a piece of paper she's going to hand out to you, and I'm going to let you pause the video, hand out those papers, and then go ahead and start it up again. Okay, so your objective, if you remember at the beginning of the slides, I told you your objective was for you to be able to explain how molecular attraction interacts with energy transfers to determine whether or not a phase change will occur. I have a question for you, and this question is, it's not worded exactly the same, but it's one of your short answer questions on your test. And I'd like you guys on this piece of paper to write an answer for me, okay? This is going to determine whether or not you understand. And what I'd like you to do is, when you're finished, you're going to give these to Mrs. Kreifels. Mrs. Kreifels, if you would please just kind of read it real quickly. And if you feel like they are okay, then great job. If not, I would like you to kind of talk with the student a little bit and make sure that they understand what's going on so that they can be prepared for the test on Wednesday. Okay? So you guys, we have these two substances, substance A and substance B. Both substances start out as a liquid. If you need to visualize this, if you're a visual learner, if you're a kinesthetic learner, think about the video that I showed you. Substance A on the left was the methane, and substance B on the right was the water. Okay? They both start out as liquids. energy is transferred into both for, let's say, 6 hours. It is the same amount of energy, same amount of liquid, same containers, everything is exactly the same. After 6 hours, substance A is now a gas, and substance B is a liquid. Explain why. I'll let you pause the video, and when you're all done, come on back. Okay, you guys, that's it for the lesson for today. Don't forget that you're going to have your end of the unit test on Wednesday. You are going to use the rest of the class to, number 1, read and annotate the article liquid oxygen. This is in Amplify, and it's in 3.2. Actually, it's 3.1.2. I'm going to change that. Let me show you where it's at. If you guys go into your Amplify curriculum, and you're right here, you're in Chapter 3, Lesson 1. It's Activity 2, and it's active reading liquid oxygen. So you're going to read, yikes, let me get to it. You're going to read this article. I think they're about 4 pages. It's a little bit long. Here's the link to it. I want you to read it and annotate it. Don't forget to annotate. That's the big important thing. So think about specifically with this one, your focus is on molecular attraction. Okay? So you're going to read and annotate liquid oxygen. This is something that I'm going to ask for on Wednesday. It's worth 10 points. Complete any late or missing homework, please. And because Wednesday's the last day I'll take it. Once you take the test, I'm not taking any missing or late homework. You can create flashcards to study your vocabulary words and your key concepts. Go ahead and you can make a Quizlet. You can just take some paper and do it, whatever you want to do. And then don't forget to study the graphic for changing phases. That was the one with the arrows, where there was an arrow going one way and an arrow going another way. I had you guys take a picture of it, and I told you that I was going to give you a pop quiz, but then we had snow days and I never got a chance to do that. So look in your pictures. It's in your photos. And if somebody has it and somebody else doesn't have it, then maybe you guys can send it to each other, okay? All right, you guys, send me emails if you have any questions. Otherwise, I'll see you on Wednesday. Thank you so much. Good work today.